In the last video, we saw that if we have three simultaneous equations in three unknowns, then we can sometimes, but not always, solve the equations using a matrix method. In this video, we're going to look at a different way of attacking the solution of three simultaneous equations in three unknowns, which will always work for the equations. Now, just to remember a piece of work that we came across in Unit 1, we discovered that the equation ax plus by plus cz equals alpha represents a plane in 3 dimensions, and the plane has got a normal vector of ABC. If we've got a system of 3 equations of the form ax plus by plus cz equals alpha, dx plus ey plus fz equals beta, gx plus hy plus iz equals gamma, then these 3 equations represent 3 planes, pi 1, pi 2 and pi 3 we could call them, and these 3 planes can intersect in a variety of different ways. We can see from the diagrams that the 3 planes can meet in a point, in which case there is a unique solution to the equation, to the system of equations. All the 3 planes can meet in a line, in which case there is an infinite number of solutions to the system of equations. Or, if 2 or more of the planes are parallel and distinct, then there will be no points of intersection of the 3 planes. Or, if the 3 planes are not parallel, then the 3 planes are going to form a sort of tent or a wedge shape. We'll now move then to the process by which we are going to solve our simultaneous equations. And we're going to find the solution by the method of first of all reducing the equations to what is known as echelon form, and then using a process known as back substitution. The reduction to echelon form is the process of moving from a 3 equations in 3 unknowns to the point where we have 1 equation in 3 unknowns, 1 equation in 2 unknowns, and 1 equation in just 1 unknown. And then, using the process of back substitution, we work back up those 3 equations to find each of the unknowns. So let's see this in terms of the example that we've got here. So, starting with the equation, x plus 3y plus 2z equals 10, 2x minus y plus 3z equals 22, 4x plus 5y minus z equals 2. The first thing we must do is to select one of the equations which is going to be fixed. And in this case, I'm going to select equation 1. That is the first of the 3 equations. And I'm going to use this equation to eliminate one of the variables from the other 2 equations. Since equation 1 has got just a single x in it, it's by far the easiest thing to try and eliminate from equation 2 and equation 3. I could eliminate x from equation 2 by taking equation 2 and subtracting 2 times equation 1. Now, when we're writing these out, it's a very good idea to set up a procedure of telling the person what you are doing. So, having some sort of shorthand. And the shorthand here I've got is I'm taking equation 2 and subtracting 2 times equation 1, which is going to give me 2x take away 2x, which is 0, minus y take away 2 times 3y is minus 7y. 3z take away 2 times 2z, which is minus 4z, so that's going to give me minus z. and 22 take away 2 times 10 leaves me 2. So I'm going to have minus 7y minus z equals 2. To eliminate the x's from equation 3, I'm going to take equation 3 and subtract 4 times equation 1. So we're using equation 1 each time in this process of obtaining two equations in two unknowns. So we've got equation 3, take away 4 times equation 1. 4x, take away 4 lots of x, gives me no x. 5y, take away 4 times 3y, is going to give me minus 7y. Minus z, take away 4 times 2z, is going to give me minus 9z. 2, take away 4 times 10, is going to give me minus 38. So my result of doing equation 3, take away 4 times equation 1, is going to be minus 7y minus 9z equals minus 38. So I've now got one equation in 3 unknowns and 2 equations each with 2 unknowns in them. The second step now is to select another equation to be fixed, and in this case we'll take it as being equation 2, and use this one to eliminate a second variable from the final equation. I'm going to choose y in this case, simply because I've got the same number of y's in my new equation 2 and my new equation 3. So all I need to do to eliminate y from equation 3 is to take my new equation 3 and subtract my new equation 2. If I do that, I've got minus 7y minus minus 7y gives me 0y. I've got minus 9z minus minus z, which gives me minus 8z, equals minus 38, take away 2, which is minus 40. So at this stage, I now have the 3 equations in what is known as echelon form. I have equation 1, which has got 3 unknowns in it. I've got equation 2, which now has just 2 unknowns in it. And my third equation has just got the 1 unknown in it. So we know that going through the reduction to echelon form gives me those 3 equations. The back substitution now is very easy. Starting with the equation with just 1 unknown, we work back up through the echelon form to find the values of all 3 variables. The equation with 1 unknown, I've got minus 8z equals minus 40, tells me that z must be 5. Substituting that into the second equation, I've got minus 7y minus z equals 2. So that now tells me that minus 7y take away 5 is equal to 2. In other words, minus 7y equals 7, so y must be minus 1. And then substituting these values into the first equation, we've now got x plus 3y plus 2z equals 10, which becomes x minus 3 plus 10 must equal 10. So x must equal 3. So we've got the solution of the simultaneous equations is x equals 3, y equals minus 1, z equals 5. And we can say that the planes x plus 3y plus 2z equals 10, 2x minus y plus 3z equals 22, and 4x plus 5y minus z equals 2, intersect in a single point with coordinates 3, minus 1, 5. Now at this stage, I think it would be a good idea for you just to pause the video and have a go at these two examples. And I would like you to solve these two examples by using the method of reduction to echelon form and back substitution. So, moving on, recall from the previous video that the inverse matrix method for solving simultaneous equations only works for systems of equations whose matrix is non-singular. In other words, the determinant of the matrix is not equal to naught. And that it required a huge amount of work to actually determine the inverse matrix. We also noticed in the previous video that if we had the equations 2x plus y minus 3z equals 0 and x plus y plus z equals 3 and 5x plus 3y minus 5z equals 3, then the determinant of the matrix was 0, so the inverse matrix method won't work. But we asked the question, does this mean the system of equations has no solutions? And we very quickly came to the observation that x equals 1, y equals 1, z equals 1 will certainly work for that system of equations. So, the big question now is, will the method of reduction to echelon form and back substitution solve these equations for us? So, here we are. Here's the system of equations again. Okay, so we're going to do our reduction to echelon form. And this time we're going to do it in order to eliminate y from each of the other two equations. So we'll keep equation 1 fixed, but we'll eliminate y from each of the other two equations because it's simply easier to eliminate y from the other two equations than it is to eliminate x or z from the other two equations. So to eliminate y from equation 2, I'm going to need to take equation 2 and subtract equation 1. So that is going to give me x take away 2x is minus x, y take away y is 0, z minus 3z is going to be plus 4z equals 3 take away 0, which is 3. So I've got minus x plus 4z equals 3. And now I'm going to eliminate y from equation 3 using equation 1. So I need to take equation 3 and subtract 3 times equation 1. So I've got 5x take away 6x, which is minus x. I've then got 3y take away 3y, which is 0. I've got minus 5z take away minus 9z, which is going to give me 4z. And I've got 3 take away 3 times 0, which is 3. So the result of doing this is I get minus x plus 4z equals 3. Now at this stage it's important we keep to the process. So what we're going to do now is we're going to fix one of these two equations and decide to use it to eliminate another variable from the third equation. So in this case I'm going to keep equation 2 fixed and use it to eliminate a second variable, in this case x, from the final equation. To eliminate the x's from equation 3, I need to take my new equation 3 and subtract my new equation 2. And if I do that, I've got minus x minus minus x is no x. Now that I knew was going to happen because that was the whole purpose of the procedure, was to eliminate x. But what happens when we take the new equation 3 and subtract the new equation 2? What happens to the z's? Well, we've got 4z, take away 4z, which gives me 0z. And I've got 3 take away 3, which gives me 0. So I've got 0z equals 0. That's really important at this stage. We realise why we have got rid of the x's altogether, but why we needed to keep track of the z's. The reason for this is we selected equation 2 to be fixed, and we decided to use this to eliminate a second variable, and we decided that we were trying to eliminate x. To eliminate x, we needed to do the new equation 3 take away the new equation 2. As a result of this process, we ended up with 0z equals 0. And it's absolutely crucial we write this 0z equals 0 down. So we have as our echelon form 2x plus y minus 3z equals 0, minus x plus 4z equals 3, and 0z equals 0. Well, 0z equals 0 is the first equation we need to use in our back substitution. And 0z equals 0 means that z can be absolutely anything at all. So we're just going to say let z be anything at all. We'll call this any number at all, lambda, for the sake of argument. If z is equal to lambda, then working up through the back substitution, I've got minus x plus 4z equals 3 tells me that x must equal 4z minus 3. In other words, x must equal 4 lambda minus 3. And working back to the top equation now, we've got 2x plus y minus 3z must equal 0. So y must be 3z minus 2x, which is 3 lambda. Take away 2 lots of 4 lambda minus 3, which simplifies down to 6 minus 5 lambda. So the solution of the simultaneous equations is x equals 4 lambda minus 3, y equals 6 minus 5 lambda, and z equals lambda, where lambda can take any value at all. Now, if we go back to our Unit 1 work, we know that if we've got x equals 4 lambda minus 3, y equals 6 minus 5 lambda, and z equals lambda, we could write that as being x equals xyz equals minus 3, 6, 0 plus lambda times by 4 minus 5, 1. And that is precisely the vector equation of a line passing through the point minus 3, 6, 0, and with a direction vector of 4, minus 5, 1. If we think about the normals of the three planes, well, the normals of the three planes are the coefficients in front of the x, y, and z terms in the equations of the three planes. The normals are 2, 1, minus 3, 1, 1, 1, and 5, 3, minus 5. No two of these vectors are parallel, so no two planes are parallel, but the planes meet in a common line. So we're in a situation where we've got a diagram something like this for the intersection of the three planes, with a common line as the points of intersection. Now let's make just a small change to the set of initial conditions. Okay, so got exactly the same set of equations as before, except the final coefficient has changed to 8. Going through the process of reduction to echelon form exactly as before is going to lead me to that. And then final stage gives me that. And this time, my final stage gives me the equation 0z equals 5. So my echelon form has given me the equation 0z equals 5. The equation 0z equals 5 has no solution at all. There's no value of z for which I can have 0z equals 5. So the equations 2x plus y minus 3z equals 0, x plus y plus z equals 3, 5x plus 3y minus 5z equals 8 have no solution. We say that the equations are inconsistent. So geometrically what's going on? Well, the planes with equations 2x plus y minus 3z equals 0, x plus y plus z equals 3, and 5x plus 3y minus 5z equals 8 have no intersection. The normals of the planes are that no two of those vectors are parallel, so no two planes are parallel to each other. So we're in the case where we've got three planes with no points of intersection. So we're in the case where the three planes are doing something like that and forming a tent shape or a wedge type shape. So, in general, if we have M as a 3 by 3 matrix and the system of equations M times XYZ equals PQR is being solved, then if the determinant of M is not equal 0, the equations are consistent and have a unique solution which can be found either using an inverse matrix method or on your calculator if you've got a suitable one, or by the method of reduction to echelon form followed by back substitution. On the other hand, if the determinant of M is 0, then the equations must be solved using reduction to echelon form followed by back substitution. The equations will either be consistent, in which case I'll have an infinite number of solutions, or the equations may be inconsistent and have no solution at all. So as an example, consider the matrix A, which is 1, 1, minus 1, 1, 2, minus 3, 1, minus 1, alpha, and the system of equations x plus y minus z equals 1, x plus 2y minus 3z equals 2, x minus y plus alpha z equals beta. We've got to find in terms of alpha the determinant of the matrix, and we've got to find the value of alpha for which the matrix is singular. And then in part B, by reducing the equations to echelon form, we've got to solve the equations in each of the cases alpha equals 2 and beta equals minus 1, alpha equals 3 and beta equals minus 1, and alpha equals 3 and beta equals 3. So, starting off, to find the determinant of the matrix, we simply write down the matrix and then repeat the first two rows underneath, and then use our diagonals. So we've got the first diagonal is going to give me 2 alpha when I multiply the numbers on it. Second diagonal is going to give me 1, and the third diagonal is going to give me minus 3. Going down the negative diagonals from top right to bottom left, the first one gives me minus 2, the second one is going to give me 3, and the final one is going to give me alpha. So the value of the determinant is 2 alpha plus 1 plus minus 3. Take away minus 2 plus 3 plus alpha, which simplifies to alpha minus 3. The matrix is singular if its determinant is 0. So for the determinant to be 0, I've got alpha minus 3 equals 0, so alpha must equal 3. Reducing the equation to echelon form, we've got to solve the equations in each of the cases. So, there are my three equations. I'm going to keep equation 1 fixed, and I'm going to try and eliminate x from equations 2 and 3. So, making my method clear again, the first thing I'm going to do is I'm going to take equation 2 and subtract equation 1. So the x take away the x gives me 0, 2y take away y just gives me y, minus 3z minus z gives me minus 2z equals 2 take away 1, which is 1. So I'm going to end up with y minus 2z equals 1. Taking equation 3, now again I'm looking to eliminate x, so I need to take equation 3 and subtract equation 1. And if I do that, I'm going to get x take away x is 0, which is exactly what I wanted, so I'm not even going to write that down. Minus y take away plus y is minus 2y. And then I've got alpha z take away minus z, so that's going to be plus alpha plus 1 z equals beta minus 1. So we've got minus 2y plus alpha plus 1 z must equal beta minus 1. Now to complete the reduction to echelon form, I need to take one of these two equations and keep it fixed. So I'm going to keep equation 2 as being fixed. I'm going to eliminate one of the variables from equation 3. I'm going to eliminate y because it's easier to eliminate than z would be. So to eliminate y from equation 3, I'm going to need to take equation 3 and add 2 times equation 2. So that's going to give me minus 2y plus 2y, which is the 0y that I was aiming for. Then I've got alpha plus 1 times z plus 2 times minus 2z. So that's going to give me alpha minus 3 lots of z equals beta minus 1 plus 2 lots of 1, which is beta plus 1. So I've got alpha minus 3 times z equals beta plus 1. So I've done my reduction to echelon form. So in the first case, if alpha equals 2 and beta equals minus 1, then my echelon form is x plus y minus z equals 1, y minus 2z equals 1, minus z equals 0. So going back through that, I've got z equals 0, and if z equals 0, I've got y equals 1. And back to the top equation, if y equals 1 and z equals 0, then x is 0. So I've got the solution x equals 0, y equals 1, z equals 0. If alpha equals 3 and beta equals minus 1, then my echelon form reads x plus y minus z equals 1, y minus 2z equals 1, and 0z equals 0. That means that z can be absolutely anything. Let's call it mu this time, just for a change of Greek letter. If z is mu, then y is 1 plus 2z is 1 plus 2 mu, and z is going to be 1 plus z minus y. So that is 1 plus mu, take away 1 plus 2 mu, which leads me to simply minus mu. So this is the case where I've got an infinite number of solutions. X is minus mu, y is 1 plus 2 mu, z is mu, where mu can take any value at all. If alpha equals 3 and beta equals 3, then the system of equations becomes x plus y minus z equals 1, y minus 2z equals 1, 0z equals 4, which is impossible, so we can simply say that the equations are inconsistent. So at this stage, with another exercise of a few questions for you to work on. And in this case, you will find that some of the equations end up to the sort of 0z equals 5 or 0z equal 0 situations where you're going to have to be a little bit careful. So pause the video and have a go at least a couple of these questions. Okay, now the final thing we want to just point out is that in fact they're using a reduction to echelon form method to find the inverse of a 3x3 matrix. So let's suppose that we've got the matrix 2, 1, 1, 4, 3, 5, 10, 7, 13. So what we're going to start off with is just observing that the determinant of this matrix is 4, so we can be certain that the inverse does exist. So what we're going to do is we're going to use a reduction to echelon form and back substitution to solve the system of equations 2, 1, 1, 4, 3, 5, 10, 7, 13 times by x, y, z equals PQR. Okay, so they're the equations in their equation format, and we've done the first stage of the reduction by echelon, reduction to echelon form by eliminating x from equations 2 and 3 and keeping equation 1 as our working equation. And then again we'll eliminate y from equation 3. So we've now got our echelon form. We've got 2x plus y plus z equals p, we've got y plus 3z equals q minus 2p, and we've got 2z equals r minus 2q minus p. So going through the back substitution now, we can say that z is minus a half p minus q plus a half r. Y is q minus 2p minus 3z. And if you follow through the algebra on that, you'll find that that is equal to minus a half p plus 4q minus 3 over 2r. And then, going back to the first equation, we've got x is a half p minus a half y minus a half z. And substituting in the known values of y and z and simplifying, we obtain x equals p minus 3 over 2q plus a half r. Now, we know we started off with the equation m times xyz equals pqr, and we know that the solution of that equation is xyz equals m inverse times pqr. What we've just shown is that xyz is in fact p minus 1.5 q plus a half r for x, y is minus a half p plus 4q minus 3 over 2r, and z is minus a half p minus q plus a half r. In other words, we've got xyz is 1 minus 3 over 2 a half, minus a half 4 minus 3 over 2, minus a half 1, 1 half, times the vector pqr. But we know that xyz is m inverse times pqr. Deduction is m inverse is this matrix 1 minus 3 over 2 a half, minus a half 4 minus 1.5, minus a half 1 a half. So by reducing this system of equations to echelon form, we've actually been able to find the inverse matrix. And this method of finding the inverse matrix is particularly useful if we start getting to much larger matrices. So instead of having 3x3 matrices, we might have 4x4, 5x5 matrices. So it's worthwhile just realizing that it does give us an alternative way of finding inverse matrices. And that concludes our video on looking at the solution of simultaneous equations of 3 unknowns.